goes. All right, so on screen 2, this is our vocabulary for this lesson. Absolute value functions. So characteristics of y equals the square root of x. It looks like this. Okay, there's a vertex of this graph at the origin 0, 0. The domain, all the possible x values are all the real numbers. Okay, and the range, all the possible y values are every y value greater than 0. Okay, there's no negative y values in this graph. If you want to describe how the function is increasing or decreasing, it decreases when x is less than 0. So everything to the left of the y-axis, it is decreasing, and it's increasing for everything to the right of the y-axis, increasing. And behavior as x approaches positive infinity and negative infinity, the ends approach positive infinity, which basically says the same thing as how they increase and decrease. Okay, but there's nothing happening right at the vertex, at the point 0, 0. We're neither increasing nor decreasing. So this is the most basic absolute value function. Okay, it's basically a piecewise function, which we're going to learn more about this week, piecewise functions. This means a function that's broken into pieces. And so f of x, a function of x, the absolute value of x, okay, when x is greater than or equal to 0, we just get x. X is less than 0, we get negative x. So when you're doing absolute value, if you're taking the absolute value of a positive number, you just get that positive number back. If you take the absolute value of a negative number, you get the positive version instead. It can also be thought of as how far away from 0 is that number. Distance from 0 is another way to think of absolute value. All right, so we're going to go to the third slide, and we're going to be able to type on here. So I'm going to show you what to type, and then you guys are going to be doing this with me on your own slide. So we want to understand the parent absolute value function. F of x equals the absolute value of x. That's this right here. And so we're going to start by completing a table of values, and then we're going to plot these points on this graph and connect them, and then answer question 3 about the graph. So when you fill in a table of values, you take the x value that you're given, you substitute it into the function, and the output is what you get. So you do have this little keyboard that pops up, keypad. If you click that, it's going to give you some different tools to use to type. So if you wanted to do the absolute value symbols, it would be this button with the A in the middle. And then if I wanted to replace the x with -3, just type it and then come out of that and then hit equals. The absolute value of -3 is going to be +3. Now you don't have to write that out every time, but you can if you want to. You can also just do it in your mind. So the function of x when x is -2, absolute value of x is +2. If it's a negative, it turns positive. -1, the absolute value of -1, +1. Absolute value of 0. Okay, so if you think about it in the terms of absolute value is distance from 0, how far away is 0 from 0? It's there. It's absolutely there. So just 0, 0, 0. Absolute value of any positive number is just that number itself. So the absolute value of 1 is 1. Absolute value of 2 is 2. And the absolute value of 3 is 3. So now I have some coordinates that I can use over here to plot some points on this graph. And so you're going to use, it's already highlighted, the pencil tool. You can change the color that you're working with. You can change how thick your line is. Okay, I'm going to start plotting points. So the first point is at -3, +3. So starting at the origin, if I go to -3 along the x-axis and then go to +3 and make a point, there's the first ordered pair, -3, +3. If I look at the next ordered pair, -2, +2, again, start at the origin. You go side to side first, and then up or down, and then make your point. -1, +1. 0, 0. 1, 1. So now we've switched directions. We're starting to, instead of decreasing, we're starting to increase. 2, 2. 3, 3. Okay, so those are all the points that I came up with. There's an infinite amount of points whenever you make a graph, but these are enough for me to then use the line tool and connect these points with some sort of a line, best I can. Same thing over here. You can add arrows to the end, show it goes on forever. And you can also check your sketch. So if I click this blue button at the bottom, it's going to show me what the graph really looks like to see if I did it correctly. And it's the red line that shows up that I can't really see because it's underneath my purple line, but I did graph this correctly. So this is the graph you want to have. This is the parent absolute value function. And then our third question on this slide, the vertex of an absolute value function is the single point that both rays have in common. So we can describe the graph of an absolute value function as a set of two rays coming from the same starting point. In this case, it's 0, 0, the origin. And if you submit it, it'll tell you you're right or wrong. I did not like that. No, that's the right answer. They didn't want me to have any spaces. They didn't like the spaces, so. Sometimes Desmos is a little picky. If you type in the origin with a space, it's going to say you're wrong. But if you don't put spaces, then you're doing a good job, apparently. All right. So this is the information we should have down for that first slide of ones that we start, doing some work on. This is slide 3. And so I can see I have 10 of you guys on slide 3 right now. I go to my summary. Hugo, you're still on the first slide. Ashley, I think you left. And there's a lot of people that still need to join. So if you're in the meet, you should be in the Desmos as well. So Callie, you need to join. Maddie, you need to join. Jalen, you need to join the Desmos. Isaac and Joseph, I need you to join. Diana, please join. Isabella, please join. So some of these students aren't in the meet at all right now, but if you're in the meet, you should be on this Desmos. Hermosa, so you're in the meet, so you want to join this. Okay. Thank you, Maddie. Thank you, Isaac. I'm going to go back to just showing the work for slide 3. Make sure you have that all copied down onto your slide. right. So let's go ahead and move to the next one, our next screen, our slide, the fourth one here. And so we're going to identify the characteristics of the f of x equals the absolute value of x function. First question here, what is the domain? Okay, and so the domain is all the possible x values. So if I'm just looking at this graph here, because it continues on forever in both directions, all the x values are possible. So this is when we would say that x is all the reals, or you can even put it as, I'm not really sure what Desmos wants me to write to make it correct on their side. So I'm just going to say all the real numbers, and you can write that too, but it probably will tell you you're wrong just because of the way this was created. But that is the correct answer. It's all the real numbers. That's your domain. Your range, though, is a little limited. Okay, it's not all the real numbers for the range because we're never down here in the negatives. We're at 0 and above. So the range for all the y values is y greater than or equal to 0. Now, if you want the greater than or equal to symbol, click on the keypad, then you can get the symbol there. And when is it increasing and when is it decreasing? So again, let's look at the picture. Well, it's increasing when I'm moving from the origin to the right. This is an increasing function here. But as I move from the left to the right, this is a decreasing function. So it's limited to the different values of x when it's increasing and decreasing. So it's increasing when x is greater than 0. It is decreasing when x is less than 0. Notice we don't have the or equal to symbol on either of those because at 0, the function is neither increasing nor decreasing. Okay, so we're going to move forward to the next slide, or screen 5. And there's nothing for you to write on this one. You can write on it if you would like to, but you don't have to. And so, just looking at the summary here, so the dots mean that you're working on it. The line means it's just an image. You don't have to write anything. If it's correct versus wrong, that like the X or the dot could come up, but you're not being graded on this. This is just for a lesson. So don't worry about if there's an X or a dot, but you should have one or the other. It shows you're participating. I'll go back to this one here. So transformations. We were doing transformations of quadratic functions before we did the MDTP. And we had a very similar looking setup for that. We had an A in the front. We had x minus h. It was in parentheses and it was being squared. And then we have plus k here. So we still have these same variables, a, h, and k. And they do exactly the same thing as they did before. The a will stretch or compress your graph. And if a is negative, it will reflect it over the x-axis. Okay, so that was the same thing a did before with quadratic functions. Here, h, this tells us if we have a slide either to the left or the right of the graph. Again, it's minus h like it was before, so you always have to think about choosing the opposite sign of what you see. And then plus k, if something's being added here, this is a vertical translation, so either sliding it up or down, depending on if it's positive or negative. Okay, so screen 6, graphing translations of absolute value functions. So we're going to graph the absolute value function with respect to the parent function. The parent function is the one we looked at a few slides back. F of x equals the absolute value of x. So first thing we're going to do here is look at this function, g of x equals x plus 3 in absolute value minus 5, and determine what is h and what is k. H and k, that's the vertex of my function. H, okay, see how I have plus 3 here, but I want to know about minus h. So I think of this as basically x minus negative 3, and then that tells me that h is actually negative 3. For k, k is what's being added. So since we have 5 being subtracted, think of this as adding negative 5, and negative 5 is my k. These two values tell me the coordinates of the vertex. So if I'm using the graphing tool over here, my vertex is going to be at negative 3, negative 5. So I go to the left 3 units and I go down 5 units. And there's my vertex of this graph. Now this is just a translation, so it's just being slid around the coordinate plane. We slid the whole parent function to the left and then down. And so it's going to look just like the parent function, it's just the vertex is in a different location. And then you can use this table here to get some more points. So, you know, I can pick anything I want for x. I do want it to be something I actually graph on this picture. So right now I have already when x is negative 3, I know the value. So I want to pick an x on this side and on this side. And so maybe I'll pick something like negative 5, see what happens. If I plug that into this, I could have negative 5 in absolute value plus 3. So is the absolute value. What did it do? Okay, and then minus 5. Okay, and then it did the calculation for me. So negative 5, negative 3 is another point, which is right here. And then maybe I want to go on the other side. Maybe I want to see how about when x is 0? So plugging in absolute value, x 0 plus 3. Close absolute value by clicking out of it, minus 5. And then if I just click out of that, it's going to evaluate it for me. So another ordered pair is 0, negative 2. Now I could keep plotting all kinds of points, but they're following this pattern of absolute value. So there's a question in the chat, why is h negative here? So if I come back and look, this is looking at the function in this form. So I would have to think of it as x minus h. So here, instead of, let's just type this, v of x is equal to absolute value x minus negative 3. So I'm just rewriting what I have instead of x plus 3. Think of it as x minus negative 3 because I have to get the x and the minus. before I could pull out the h. And same thing for the k. That's subtraction. I really want addition, so I'm thinking of this as adding -5. So that's why h is -3 and k is -5. Once you have enough points here, you can do more if you want. Maybe I want to see where does this cross the axis at. A little bit closer to that. I pick like -8. And just start typing in using this keypad. So -8 plus 3. And then we're subtracting 5. If you just click out of it, it'll tell you, okay, 0. So when x is -8, y is 0. Let me just connect these with a line. Do continue on in 2 directions. And you can check your sketch to see if you did it accurately. That's pretty close. Okay, so I'm just going to leave this here for a little bit before we move on to the next one. You guys have other, would it then just be 3? What if it was shown as -3? Yes, it would just be 3 in that case. So if you had x minus 3 in the absolute value, 3 would be what h is. So Diana, you're still back on slide 1. You need to move forward to where we are. Summary. So Maddie and Hermosa, just jump forward to where we are, and then you can catch back up on those slides later that you're stuck on. And Hugo, you want to move forward to where we are? So we are going to do 2 more slides together. And then you will have a couple slides to do. And then the last one's just a feedback slide. We'll do 2 more graphs. You'll do 2 graphs, and then you have a feedback slide. All right, so let's go ahead and take a look at 7. And if I do go too fast on any part of this, it's in the video, which will be posted later, and you can go back and pause it and fill in what you missed. So graphing translations of absolute value functions. Okay. So completing the table below using the function. Here's our function. G of x is equal to x minus 4 plus 2. And so the translation, what is the value of h? So here is a case where we have x minus 4. We want minus to figure out h. So what are we subtracting? That's what h is. We're subtracting 4. So 4 is our h. Does that mean we move to the left or the right? So since h is a positive number, we're moving to the right. What is the value of k? What are we adding on? 2. Are we moving up or down? 2 is positive. That correlates with moving up. So these are the same rules for when we're doing the same kind of thing with quadratics. You can check your answers. Okay. So this is another method of graphing. Okay, so here we can see that we're taking the function and it's just being, which of these match this? Well, 4 units to the right and 2 units up. That's what we're going to be doing. So we're taking the parent function and just changing where it's at in the coordinate plane. So when you plot these points, your vertex, instead of being at 0, 0, we've translated it 4 to the right and then 2 units up. So there's the vertex of this g of x function of x, and then it's the same points, just up 1 over 1 in both directions. It continues on, and you can check it. That is where it's going to be. So you can then connect your dots and draw a little arrow. And that's another way to graph absolute value function. So that's just using the translations from this form. Do you guys have any questions about this slide or one of the past slides? So some of us are on this one right now, some of us are on 6. Maybe we're just comparing the two. So these are just 2 different methods to graph. Here, this method is find the vertex and then just make it a table of values. This other method is to recognize that the parent function is a translation compared to this one. So we just translate it based off of H and K. Another thing you could do is use Desmos, just the graphing calculator, and type it in and see what it looks like. All right, we have one more slide. So this last one we're going to do, this is graphing a absolute value function where you might have a stretch or a compression. So here is our function, g of x equals -1/2 times the absolute value of x. That's really close to the parent function, but we have this, this coefficient out here, -1/2. And so if I go all the way back to slide 5, and I look at where that a is, that's in the same place as -1/2. And so if I look at these rules here, negative means it's a vertical reflection. 1/2, okay, the absolute value of a is 1/2. That's between 0 and 1, so it's going to shrink or compress it. So that's what's going to happen to this graph. It is the parent function, but it is compressed and reflected over the x-axis. So we're going to complete the table. What is your vertex? You know, if I write this in that form with H and K, even though I don't have them, you can see they're both just 0. So g of x equals -1/2 x. Instead of x, I could put -0, right? Because you could subtract 0, and I can always add 0. So I can use that to see that h is 0 and k is 0. So my vertex is 0, 0. Is it translated? H and K are what translates it. If H and K are both 0, then no, it's not translated. Is it stretched or compressed? Yes, we just saw that. It's going to be compressed because of the negative here. No, I'm sorry, because of the 1/2 here. The absolute value of A is 1/2, which is between 0 and 1. Is it reflected? Yes, that's because of the negative. So we know the vertex is 0, 0. There's our vertex. But because it's compressed, I can't just do the basic form of it, like up 1 over 1, up 1 over 1. I can't do that. So I need to use this table and pick some values of x to see what I would get. Maybe I'll pick 2. When x is 2, if I put a 2 in here, you can even just type this out, negative 1/2, and then use the absolute value. And then instead of x, we'll put 2, and then close that absolute value. This is my answer, negative 1. So I have a point at 2, negative 1. 2, negative 1. I'm going to go a lot further out. Let's try 10. So negative 1/2. Absolute value of 10. Like out of it, we get negative 5. So if I go all the way to 10, then I'm going to go down to negative 5. Let's try some points on the other side of the vertex. Let's try negative 6. I'm just picking numbers that'll fit on the graph. There's no rhyme or reason to why I'm picking the ones I am. Just they'll fit on the graph. Negative 3. So that's another point I can plot. Negative 6, negative 3. Negative 6, negative 3. And you could keep doing more points. You don't really have to. If I check my graph before I graph it, those points that I'm plotting are right on it. If I keep picking more and more points, they're going to keep falling on this graph here. So that is my graph. It's reflected and it's compressed, just based off of the way it's written with that coefficient of negative 1/2. You multiply negative 1/2 by 6, not negative 6. Yes, because, oh, yes, you're right, Mauricio. I will change that. And there we go. Thank you. But that's why this, when you graph absolute value, it's a mirror image on either side. There's that line of symmetry. Nope, it's still going to be that. So look, let's also put in 6, the one that I made a mistake on, and do negative 1/2. Absolute value, and now I'll put 6 in. And so I get the same answer because the only difference here in my calculations is I'm taking the absolute value of negative 6 or 6, but the absolute value of both those numbers is 6. So I'm multiplying by positive 6 each time, which gives me negative 3 twice. So these two ordered pairs of ordered pairs, these two pairs of ordered pairs, yep, they're across from each other. They're the same distance from the vertex. So I also have 6 and positive, -3 in here. Okay, so this point and this point. Same distance from the vertex, same distance from the y-axis. So I'm going to turn the pacing off because when you are ready, you're going to be able to go to 9, all right, and 10. And then you have a feedback slide.